Thanks again for everyone for joining our session today. My name is Mingshi Liu. I'm a machine learning engineer in OpenSearch. I'm here today with my colleague, Praveen.
Hello, everyone. Thanks for joining. Myself, Praveen Mohan Prasad. I'm working with AWS as an analytics specialist technical manager. I am from Dublin, Ireland.
Great. We're very excited today to talk about how to unlock insights from multimodal PDF using OpenSearch and vision language models. So in our life, the documents are everywhere. Either it's from the business reports that we read online or the invoices that we got from purchases, and also the internal emails that we read every day with attachments and like policies like travel insurance policies that are usually in PDF formats. However, unlocking this information from PDF are very difficult because they also come with text, and also usually they come with charts and images. And now that we have some of the reports that have very rich visualizations, and it's becoming challenging for search to understand the content within them. And traditional search often fail to understand this rich media because in the past world, they're just trying to see, is there any text information that they can find in this rich media? If in the tables and image, they don't contain much of the text, it was very challenging for those to understand. So how can we understand PDF better? We're going to solve this problem today. I'm going to bring up this concept again, RAG. If you're listening to Eric talk this morning, he was presenting RAG in a chatbot. These are very trending words in the last couple of years in agents and building chatbot systems. In RAG, it first retrieves the relevant information, and then we serve as a context, argument it into the prompt, and generate the final answer. This is a very common concept nowadays. How to achieve RAG in OpenSearch. This is one of the high-level architecture. We have a lot of different ways to implement them in OpenSearch, but this is a general way of implementing them. So we first, users will send in a queries, and when the queries comes, we'll try to use embedding models to embed this query string into vectors, and then we use a vector store. In this case, is OpenSearch. Then we retrieve the relevant document as a context that is coming additional context, sending to the prompt, and argumenting the prompt. When LLM gets it, the large language model, also known as LLM, that gets it, will follow the prompt, understanding the context, and generate the final answers. In the RAG applications, we will need two models, right? In this case, we will need embedding models and also a large language models. How to achieve the RAG applications? ML integrations makes it very easy in OpenSearch. You don't have to generate the embedding outside of OpenSearch. You can also try it within OpenSearch. How does that happen? So we have ML connectors. So by using these powerful ML connectors, you can choose either you want to have a customized model or you want to use dense embedding models or sparse embedding models. You can choose to connect with the remote model services. For example, SageMakers or Bedrock or OpenAI, it's up to your choice to choose which remote model service that you want to connect to OpenSearch. Or OpenSearch also support local model, so you can choose your models connected to OpenSearch, register it, then you have the model ready for OpenSearch. Now that you have the model ready, then you can start thinking about ingest the documents. So I want to introduce a concept called ingest pipeline. In ingest pipeline, you can configure when you're preparing your index. When you configure your pipeline, you can think about you can use multiple ingest processors. So for example, if you want to think about running a model prediction, you can use ML inference ingest processor. They will allow you to invoke any of these models and run predictions, and also add your prediction results along as new fields into your document. Thinking about vector stores, it's very common that you would like to have your text prepared with your embedding vectors. In this case, you can use an ML inference processor to invoke an embedding models, and then get the vectors stored as a new field called maybe text embedding fields. Then you will have the embedding ready for your vector search. Even when you have a very long document, for example, you can think about, okay, I want to apply chunking strategy, then you can first think about using a trunk processor first. It's like a very long document into different chunks, and then you can run an ML inference processor for each of the chunks to generate text embedding for it. So ingest processors are designed to be lightweighted, and you can train them and then group them together to serve different purposes. If you have local models, you can also try out embedding processors. And ingest pipeline is very easy to use. Once you configure it once, you apply it into your index setting, and then when you run your ingesting calls, it will auto-apply in your every ingestion actions. So once you have your document ready in your OpenSearch cluster, you can think about, I want to use this index in search. In search, we have very similar concepts. Search pipelines is the same that you can use multiple processors. So back to RAG applications. You can achieve your RAG using ML inference processor in search pipelines. Earlier, we were thinking about we need an embedding model. Then when you're using ML inference search request processor, you can invoke an embedding model. Then it will help you to convert your query string into text embedding string. And then you can later use it for better search. And now that we get the content back, and when you are talking about using RAG, you need a large language models to understand your content, argument the prompt, and send it to large language model. Now you can have another ML inference processor, and this one will invoke the large language model. Then it will generate the final answers for you. So it depends on your use case. There are a lot of different processors you can use in search pipelines. If you like to re-rank your search hits, you can use re-rank processor. If you like to normalize your score, you can also try normalizing processors. In here, we try to attach the supported connectors QR code in here so that you can try to see what are the blueprints that we are supporting now. Then you can select and see which other model you want to try it out and see. You can build out your own RAG applications. So this is the QR code that you can try it out and see what are the models that interest in your use case and see if you can build out RAG applications. So with these capabilities, you can build up RAG, but like we were just talking about, many of the people use RAG for text, and they usually ask questions in text and get back the answer in text. Now that I want to understand PDF, and like we said, they are usually in multiple modals. And how do we solve this? How can we let the RAG understand PDF? We would like to introduce multimodal RAG. In today's sessions, we are going to introduce two approach that how we can implement multimodal RAG. The first one is we are trying to ground different multiple modalities into text, meaning that if it's multimodal, if it's image, we'll try to generate image caption. If it's a table, we try to generate table summary. Then now that we have different modality into textual formats, then it's easier for the later RAG applications. And the second approach, we'll try to use a new one. This second approach, Praveen, we're going to introduce later, that we are trying to use vision language model. And in this new model, it not only has understanding in text, but also it can understand text and image jointly. So we will explore these two options in these sections. So before we talk about how to implement the RAG, a multimodal RAG, we will try to give you a demo and see how this multimodal RAG works on the web applications. So I'm going to show you this website. That this web application is built up by Praveen. And we have an example of the PDF file here. It's called UK Housing. So I opened it on the side, but you can see it's a really long one. I'm not going to read line by line. But we want to test it out in using multimodal RAG. How does this web applications can understand my PDF file? So let's test it out and think, I'm going to ask, what city has the highest average housing price in UK? Noting that in this question, I don't have a hint about which city, but it looks like, okay, the answer is telling me the highest average housing price in UK is London with an average price. And I wonder how it gets out the answer. In this web application, it will also show me the relevant source on how it gets the answer. So it gives me an image that it looks like, okay, this is from a table. And it was able to capture within the PDF. We can try to go back into this PDF, and I don't have to read it through, but I can skim it through. Okay, this is the table that the web application which implements multimodal RAG, it was able to find out in this table, even though it doesn't have the words highest, So, but it was able to compare the pricing in the numbers and find out London has the highest housing price, and it was able to understand this table that this highest amounts of housing price is belonging to London. So in this web application, it looks like it's not just looking within the PDF file and looking for the match for text. It was able to understand the table, doing some calculation, and find out the city London has the highest housing price. So this is one of the demo that we want to show you how a multimodal RAG can understand PDF files. So going back, how can we achieve multimodal RAG? Let's go to the first approach when we are trying to do grounding multimodality into text. So the first step that we need to do is we think about when you have one page of PDF, which part of it is a tables. We try to convert it as a CSV string. So some part of it is a text, a really long text. Then we try to apply a trunking strategy to make them into smaller text chunks. And then we identify, is there any images in this page of PDF? If it's an image, we try to extract them out, crop them into a single JPG file as an image. And then we can prepare later for our next step. So in the extraction phase, in how we build our website demo, we use unstructured Python package. But in the world now, we actually has a lot of extraction tools that you can use. You can choose a Llama parser. You can also choose Google AI document. You can use Amazon text extract. Those tools will help you extract different components from PDFs easily. If you want to try it out, how to build it out in OpenSearch, we can try the ML integration that I just explained. If you want to use in these tools using Amazon text extract, you can register a connector connected to Amazon text extract, have a model deployed, and then when you're invoking the model, you want to bind it with ML inference processor. So during ingest, this ingest pipeline will work, and then it will text extract and save the different components into your documents together. So this is one way of doing so. If you are using AWS versions, then you can try to use, there is a Amazon's Bedrock automations that will do the extraction work for you. So you just have to go to Amazon Bedrock Data Automation, try to drop your PDF and extract different components. Then you can choose to select Amazon OpenSearch services to store your extracted components. If you are using open source, if you're a heavy open source user, you can also try out Arrange Doc Parser. It also will do the extraction work, and they have a really direct connection into OpenSearch. So this is also the alternative ways that you can consider about on the extract phase. After we are done with the extraction, now that we have different modality extracted out in different batches, then we want to do the transformation. So for images, we try to generate the textual formats from image. So how do we do that? We can also use the ML integrations that I just talked about, that you can have an ML inference processor, and then you connect it to a large language model. For example, we use a Claude 3 Sonnet that we just have to give in the prompt and saying, hey, I want to see what's in the image. Then Claude 3 will give me the image captions and generate it. Once we have the image caption generated, we can use Titan embedding models. And how we invoke them is similarly, we use ML integration. So in the first one, we have a Claude 3 models in ML inference processor that will generate the image caption. And then we use another ML inference processor for the text Titan embedding models to generate embeddings for you. Now, in this ingest pipeline, you have extracted components. You also have your text embeddings fields. Then you can store into your index. Similarly, for tables, we can use the same pipeline. So this is ease of use. Then you can have, remember earlier, we extract the tables into CSV string. Then we can use the same large language model like Claude 3 models. You can ask it to generate a table summary, and then using a second ML inference processor to generate the text embedding for you, and you can store the text formats and also the text embedding into your index. Now that we are done with the extraction and transformation, we want to give an overview of how this multimodal RAG work. So earlier, remember, we have a list of documents of PDF. We try to extract them out into image and text and tables. For image, we try to generate captions. For table, we try to generate the table summaries. Now that we have textual formats for each of the modality, we generate the text embedding for them, and we store them on the same field, text embedding field. Now that we prepare the vector fields ready, then we can use similar RAG application architectures we just talked about. Then when users are sending queries to the vector store, conduct a vector search, then it will return the context. Maybe you want to re-rank the results or do other processing, but then you have the context sent into the large language model, then you can return the generated response and back to your applications. So this is how the first approach, grounding multimodals into text, and to achieve multimodal RAG workflows. So we can think about how do you like this approach. So the biggest benefits of this first approach is you have precise controls on how you want to extract different components, how you want to pass them. So for example, if you want to generate your image caption, you can control the length of it. You can also try to apply the language translation if the tables were in different language, you want to standardize in English, you have precise control on it. Also, you can validate how well the large language model generate those image captions, and you can have precise control on each of the modalities. And it's also easier for you when to trace and debug through the captions and summary, because when you're seeing the search relevance might seem off, you will be able to see from the text summaries and image captions that are they relevant to my query strings. It's better to debug compared to the vision embeddings that it's really hard to decoding. Also, in the first approach, because we standardize different modality into text field and generated one single text embedding field, it's very simple for indexing. You have it very simple for your vector store to query, and you just have to save it as a one KNN field type, and that's it. That's the benefits of approach one, but there is also a big problem that you might also face a problem of information loss, because in the pre-processing layer that you extract them out, you transform them, then it depends on the large language model, like how well they are parsing your information, how well they transformed your table summary and image caption. Some of the very low-level details in these tables and graph might be missed. You might, so when you're asking some of the very lower details about those multimodal, you might still got some information lost. And also on this pre-processing layer, it's a really big factor to decide the quality of your data. And also when you think about pre-processing layers invoking different models, and also if your logic is very complex, it will increase your indexing runtime. And also multiple resources of running model might increase the cost. So I will give you a second to think about it, about how you like the first approach, and Praveen is going to talk about the second approach and let you to see which ones you like.
Cool, thanks Mingshi. So now we will move on to the second approach, but before that, I want to take one of the limitations that was covered by Mingshi in the first approach, which is the information loss, right? So when we are doing the parsing, when your parser misses any information, from the table or from the image, extracting that information and you're not indexing it, then you are losing that information, and finally that would totally affect your RAG's quality, right? So now, let's see with an example how we have information loss is affecting your overall response quality. OK, so for this, I'm going to use the same application, but I'm going to use a different data set. And this data set is around 7,000 PDF pages, which was created by Vespa team. And we use the approach one, grounding modalities to text, and we indexed all these into OpenSearch index using the approach that Mingshi just covered. See, one of the pages that I'm interested here is this particular page. I just took a subset of those pages here. And in this page, as you see, the chart which is highlighted, it talks about share of employees, managers, and new hires who are women in percentage, OK? So let's see, I'm going to ask a question something like, okay, what is the proportion of new female hires? Okay, yeah. So let's see like what's happening with the large language model with the approach 1, and also note that the information of women is only present in the header of the chat, but the legend doesn't say about any gender-specific things. So that's a point to be noted. Let's see how our parser, the unstructured parser, has helped with this particular extraction. So let me copy the question from here. What is the proportion of female new hires 21 to 23? And then I'm going to switch to the index that I've already indexed. Perfect. So this is going to, my index already has all the captions of the graphs and the captions of the tables and already indexed into the OpenSearch. So now we see the answer is, it says, I don't know the proportion of female new hires. And it also says that it doesn't have any information about the female new hires in that period. Okay, let's see the sources. Okay, it got the right image. My parser took the cropped this particular image, but the problem is it couldn't correlate the header with this particular image. That was the problem with my parser, where it like the first header went as a separate text chunk, and this became a separate image, and the caption does not have information of this about this female or whatever the gender is. It has information about new hires, but not any female proportion. So that was a problem that the retriever did not have the response, and RAG was not finally giving the right answer. So let's see like how we can overcome this with the approach 2, which is using vision language models. Okay, that's where we got a new model called ColPali, which was released last year. So ColPali is a vision language model which was fine-tuned for information retrieval use case. Okay, so basically you can think about, they took a vision language model, and the vision language model name is called Polygemma, and this is, again, a model developed by Google. And this vision language model has capabilities to understand images. So you send an image to it, it will be able to caption it, or if you ask a question giving an image, it can answer that particular question depending on that image. So that's the capabilities of Polygemma. They took that Polygemma model and they fine-tuned it in a way that it can provide embeddings for your information retrieval use case. Okay, so like taking all the vision understanding capabilities of a great model, fine-tuning it as a bi-encoder model so that it can provide embeddings for your documents and images. Okay, that's the overall thing about ColPali. So if we expand ColPali, it's called as contextualized late interaction over Polygemma. So how it works? So first on the offline indexing. In context of ColPali, the document is nothing but an image of a PDF page. So you take a PDF page, screenshot it, and provide as an image to the ColPali model. And internally, inside ColPali, it has this Polygemma VLM architecture. I will just quickly go through what are the different layers that it covers. But finally, what you get is vectors for this particular image, which is nothing but a PDF page. Oh. Yeah. OK. So the first step is like when you give the PDF page as an image, which is a document in context of ColPali, this image is split into number of patches. So it's 32 cross 32. You get 1,024 patches for that particular image. With additional 6 tokens, it becomes 1,030 patches per image. And all these patches undergo an encoding process where you get an embedding for every patch. You can think about this embedding is nothing but a model, like a clip, where it provides embedding for image image patch. Now, all these embeddings has image understanding capabilities, right? Because it got those embeddings from an image embedding model like clip. And then it undergoes the next layer, which is a large language model. And this large language model here, this is purely a text-based large language model. Now you got the image embeddings in here. Those image embeddings for every patch gets passed through a text-based large language model, and now it gets contextualized. That's the name contextualized here. So basically, it gets contextualized by those text understanding capabilities. Now the resulting embeddings will have both visual understanding and text understanding capabilities. And finally, you get a reduced dimension count of 128 dimensions for every vector. So you send an image, finally you get 128 dimensional embeddings, like where you have a total of 1,030 embeddings for that page, and every embedding is going to talk about some part of the page with both text and vision capabilities. That's what you get when you send a document. So you loop this process for all your document pages, but you don't have to do all of this. Like you just send it, you get a list of vectors for that, but there's just the internal happening inside ColPali. So you get all the pages and you put it into the vector store. And then comes the query side. Okay, so in the online phase, you pass a query, and this query is again passed into the text-based large language model, and you get a vector for every token here. It's not one vector, you're going to get a vector for every token based upon your text. So now you have multiple vectors for your query, multiple vectors for your image, just 1,030 here, which is somewhat like a huge number of vectors for every page. Now happens the comparison. So when you have multiple vectors both on the query and the image side, then the comparison happens on a mechanism called late interaction. So it means that every query token is going to check the similarity against every patch vector that you got from the image, and finally a score is calculated, which is based upon a formula that is written here. Okay, so I will go through this formula when I run the notebook, but basically you're going to get a score that came out as a result from doing a similarity comparison between every image patch vector and every token vector here. So there's a good interaction happening between the query and the image vector. So that's why it's called as interaction. And the late interaction meaning it's happening at the query phase. So it's like not from all the layers down the architecture. It happens only when the score is calculated. So that's why it's called as lately interacting query and the image patches. So now let's see how to use this for a retrieval. Okay, so now we have a retrieval use case, and you want to use ColPali. How do you do that? So in talking about retrieval use case, the problem that you're gonna solve is here with ColPali, finding the top pages that has relevant information for the query. You're not looking for top chunks. You're looking for top pages, which are images stored in your vector store. You're going to find top page images that has relevant information for query. That's very important. So, and rest of the thing is all a regular vector search problem. So you take all your pages, get 130 vectors per page, pass through ColPali model, index into OpenSearch, and then during the retrieval phase, you're going to take the query. Say, for example, I have a query which is quarterly relative written, which belongs to one of the PDF page. And then I pass it through ColPali model. I get multiple vectors, token-based vectors for this particular query. And then OpenSearch is going to do a KNN search, gets back the results. Based upon the results, here I'm going to do a maximum re-ranking. Here is where the cross dot product of every image patch vector versus every token vector is going to happen. And finally, I'm going to reorder those resultant documents based upon this maximum similarity score, and I get the top n pages. So this top n pages means that it has information related to your question. So that's not all right. So what if you want the exact answer? You can't be looking at those pages to find the answer. That's where we have RAG in place. So now here the problem statement is pass the top pages to the VLM, to any VLM, and ask the VLM to answer the query. Okay? So now, again, you have to recall that your top pages are images. So you have to use a vision language model for that. So now I pass the top pages to a vision language model, like anything, Claude 3 Sonnet or Amazon Nova or like any provider you have, and then pass the same question, and then you prompt it. These are the 3 images that you have that has answer for this question. Please find it. Then it's going to give the final response. So now this closes the loop of finding the exact answer for your question. OK, so now let's quickly go through a demo of how we achieved this in OpenSearch. OK, so first thing is that I want to show you how we have indexed the same data set, the 7,000 PDF pages, into OpenSearch. OK, so this is the index mapping I have. You don't have to focus on everything. Few things here. First thing is, I said, you're going to have multiple vectors for every page. And here in OpenSearch, every page image is going to be a document. Okay? So you're going to use a nested vector field where every single document is going to have a lot of KNN vector fields beneath it. Okay, so this is quite important because you have to use nested vector fields so that your retrieval jobs gets easier. One more point to note here is ingesting 1,030 vectors per page is going to increase your storage and memory footprint, right? So that's where we also you can also adopt a pooling mechanism where, in our use case, we just converted the 1,030 vectors per page into 30 vectors per page. Okay, so the authors of ColPali also say that pool factor of 3 does not reduce quality, but reduces the number of vectors by 67%. So based upon that results on their corpus, whatever they experimented, we also adopted the same. We did we tried different pooling processes, mean, max, or clustering pooling. But yeah, you have to test it on your domain data. So we just reduced it to 30 vectors per document, which is per page. And then I can quickly show you how it looks on the search side. Sorry, on the how it looks on the real document. As you see here, I have a lot of subvectors into every document. This is one single document. I have many subvectors, okay? Because of that nested field type. This is the structure you will be seeing as when you index to one single page with multiple vectors. Okay, having that said, let's jump into this particular thing, particular notebook where we will start directly from the query thing, okay? So I'm going to ask the same question, proportion of female new hires, 21 to 23. That's going to be my question. So I'm going to first encode them, converting into ColPali embeddings. So here is where I got total number of token vectors is 30, because again, for every query, you're going to have multiple vectors based upon number of tokens. Here I have 30 tokens based upon the tokenizer. So you got 30 128 dimensional vector embeddings for this particular query. Now, multiple vector retrieval problem with OpenSearch. So, few things to cover here. First we did is a mean pooling of the query token vectors. I have 30 query token vectors. I'm doing a mean pooling to get one single query token vector, like how we did pooling for the page vectors. Alternatively, you can also use a OpenSearch hybrid query where you can pool it to 5 token queries, 5 token vectors, and use a hybrid search to do 5 KNN search in parallel. That is also you can do. That's even going to be better. And the next thing is, this is the retrieval phase, okay? I'm doing a KNN search, and as you see here, I want only 20 documents. That's what my desire is, but I'm looking to retrieve 200 documents. The reason is, since I have done pooling, reduced some quality there, I'm compensating it by retrieving more, but on the re-ranking side, I'm just going to use re-ranker only to re-rank and then get the top 20 documents only. Okay, so that's where you can compensate with upsampling your retrieval size. Okay, so retriever is done, and then here is where, okay, let me run this and then keep talking. And then we have this maximum similarity re-ranking. Remember the cross product of every token vector against every patch vector, right? So I will try to simplify this. Basically, what you do is you iterate through every token vector, okay, and then you compare the current token vector with every image patch vector, perform a dot product, and then from that dot product you're going to have list of dot product scores, right, for every token, because you're going to comparing with every image vector, patch vector. Get the max similar patch for the token. So you'll be doing this for every query token vector. So you'll be getting a list of maximum scores. Then you're gonna do an addition on all those maximum scores. This is nothing but the maximum similarity ranking. Multiple vectors versus multiple vectors, how do you calculate the score? Yeah, you can also simplify this using a Python torch operation. Using it is like you can use this to reduce it, to make it like in one single line of code. But I just want to explain it how it works internally. OK, so as a result, I got top 20 pages. As you see, like every document is nothing but a page. OK, you see that I have a maximum score, and also I have an image of a page here, .jpeg file. Now let's see what is the top page that resulted from. Oh, I got the right page. From 7,000 pages, after all indexing and retrieval and re-ranking, I got the right page, which has a result. And now I'm going to do the complete circle, where I'm going to pass this top page to Amazon Nova VLM. You can use anything of your choice, and ask the same question. So here, I'm sending the image in form of a binary object, and then asking the same question, and asking it, OK, given a PDF page, answer the question. That's it. Yeah, so now you see the right result. So this is all coming from that particular graph. 46 and 21, 36 and 22, and 39% 23. We just overcame that information loss problem. One additional advantage of using this multi-vector approach, like in any model study, when you use multi-vector approach, multi-query token vectors versus multiple document vectors, you can do the interpretability of results. Why one document came as a result, you can check that, which is not possible in regular vector search. So basically, you can say, you take a token from the query and see where is the token sitting in the document, or what is, how is that, which document patch is contributing to the score. You can see that by drawing a similarity matrix. Say I'm going to draw a similarity matrix with 30 query token vectors, 32 cross 32 image patch vectors, and these are all the different tokens. And I'm interested in the token of female. Let's see where female is coming in the patch. I'm going to give the token position 5, which is corresponding to female. And then it is going to give the result. And as you see here, these are all the 1,030 vectors patches in that image, and more concentration in here, the header of the chart. So that's where the female token is having more similarity with those patch vectors around there. So that's like, so you have this interpretability of results in pretty simple words. OK, so what are the trade-offs here? It provides great quality compared to approach one. This is, again, from the research paper. And then better indexing latency, yes. But in terms of search latency and storage memory footprints, it's going to be worse than the approach one, because you're going to have more storage and memory, and latency is also going to increase. So you can use the pooling mechanism that I just told you, or also you can leverage OpenSearch quantization of vectors to reduce your memory footprints. But make sure you do this upsampling of retrieval and re-ranking so that you're compensating that particular loss with quantization and pooling mechanisms. That is something, a fix you can do. ColPali generalizes well, need to be fine-tuned for other languages than English. You get interpretability of results, that the image that I shown you, where is the result coming up. And unfortunately, now OpenSearch does not support maximum scoring, which I did in the client side, right? So we have a feature request, so please press one on that. We will show you the QR code for that. So when to use which, like on simple, ColPali is you can use it for PDF pages, RAG for PDF pages on large scale. If you have a smaller corpus, you can go with the approach one. And it doesn't support English, it only supports English language. So if you have a non-English corpus, approach one suits much. And if importantly, like if you want to do full text search on your unstructured data, in addition to RAG, then approach one is the way to go. So yeah, if you have complex PDFs compared to a lot of multimodalities and so on, then ColPali makes sense. Complex PDF, which is only in English, and you have a lot of PDF pages, then ColPali makes sense. Otherwise, you can't go with the regular first approach. So these are the QR codes. The first one is the important one. We have the feature request for OpenSearch to support maximum similarity scoring and handle multi-vector retrieval for late interaction models. So that's the RFC. Please +1 on that. Let's see this feature soon in OpenSearch. And then we have this ColPali notebook code. And finally, we have a list of tutorials for you to see how to connect extract, how to connect ML models that we covered in approach 1. Yeah. So thank you.
I'm supposed to ask for questions, but I have a question first myself, which is, what's the computational cost of the two approaches, and how large a corpus are they practical to use on?
OK, so let me go here. OK, so for the approach 1, approach 1, you're going to use a lot of models in the first place, like for image. You're going to use two large language models. One is the VLM, and another one could be a text LLM, and also embedding models. In case if you want to use multimodal embedding models, that could be an additional component. So whereas in approach 2, it's going to be only one model and an additional VLM. Okay, so if you ask me like which is like compute heavy for on the retrieval side, like on the indexing and the retrieval side, I would say the approach 1 is like computationally heavy because there's a lot of interactions happening with models, and the pre-processing layer you need a big parser also. Whereas the approach 2, the computational cost will be comparatively better because you're just doing a vector embedding. But when you
It's doing a cross-product.
Yeah. So see, for now we are doing it on the client side, right? So if we have OpenSearch, do that maximum sim scoring as a part of the node itself without moving the heavy data to the client, I think that's going to be like a re-rank processor. Like we have a lot of re-rank processors, right? So I think there is going to be little added latency compared to not doing maximum sim re-ranking, but still like answering a trade-off between your quality and your latency. I think that's going to be better when you have it in re-ranking done in the same node. So on the whole, computational cost, like approach 1 is little heavy. That's where you see the same table.
It's a little heavy compared to a plain hybrid search. Are we talking 2 times, 10 times?
OK, so see, I haven't benchmarked it based upon some number of pages. This is a table from the authors directly. For example, they did the approach 1 and the ColPali approach. So if you see that indexing latency, that's where all the computations go. Like it's 7 seconds per page in approach 1 versus 300 milliseconds in the approach 2. That itself explains how computationally heavy on the indexing side the approach 1 is.
I want to make up some additional info. So I think the experiment's result is coming from the research paper from ColPali. So this is their results. If you're doing it on your side, it might be different. And I want to point it out that even though on the approach 1, you use 3 different models, that you use embedding models, you use LLMs, and also lastly, you also use another embedding model. So one embedding on your ingest, one embedding when you search, and one LLM when you generate the result. It sounds like 3 models, but remember, 2 of them are pretty lightweight. Like text embedding model, you can use it really small on your local cluster even. So thinking about computing resources, these 2 text embedding models are pretty small. Large language model might use some more of the computing resources, but in approach 2, using ColPali, you also need to invoke ColPali model 3 times. So because it's the same process, right? You have to use a model like ColPali models for indexing. You have to use it when you are search. You also have to use it when you don't have to use ColPali model. You might want to use other like vision language model, but you also have to involve the model the third time to generate the final answer. So thinking of computing resources, when you're talking about hypersearch, I think on search side or indexing side is so fast. But running on the model side is actually taking a fairly long time and fairly big resources. So it depends on the combinations of like approach 1, 3 models that you choose, or the second time you use ColPali, you have to invoke the same model 3 times. So thinking about the resources, it depends on like how you want to choose the combination of the models on the first approach, and also on the second approach, you might get different benchmarking results.
Yeah.
I'm supposed to run to send the microphone to the right place.
Yeah, thanks for the great talk. It's really surprising that the ColPali approach seems to be, efficient compared to the other one. We can just thinking about the cross product and everything that's going on there. So very surprising. Maybe one question about the approach 1. You are talking about PDFs specifically, and there something like charts and numbered charts and references between text and charts is a very standard thing that will happen in lots of PDFs. So you might, or the authors might have thought about trying to exploit this structure as well to get this, basically with the approach 1, a success. I mean, of course, it's a good counterexample for the approach 1, but it feels like it should be possible to get at that.
You mean the approach 1? Okay.
The approach 1 plus exploiting the fact that you have a diagram and it's numbered, and then you also, so you have the reference in the text, and this is a very standard thing for PDFs. So it might be achievable, right?
Of course, see, that's definitely true. Say, in the approach 1, it's all about if you understand the complexity of your PDFs, okay, and you have a parser. Like sometimes just open source parsers itself like more suitable for your complexity of documents, right? So if you're able to somehow ingest all the data present in the PDF and have them proper metadata and index into OpenSearch, yes, like you can have the proper extents, have a proper references to the table. You can somehow make the approach 1 totally workable without missing any insights. Okay, so like we were following this approach 1, and it was working for many use cases, but it failed in few use cases. But it doesn't mean that approach 1 totally it doesn't work. So maybe we have to fine tune where it got failed, and we can fine tune the models, like whichever is supporting the caption or like the layout, and giving the parsers like better understanding of my PDF layouts. That's all gonna help. So yeah, and the important advantage here is like, for the first approach, you can also do it full text search, right? You have the metadata chunks and so on. So yeah.
I think that's a really good question, because that's exactly the trade-off that I was mentioning for approach 1. That if you're trying to, we will have very precise control of each modality if you're talking about charts. And then if you find out, okay, we find out the information lost on approach 1, then you can think about, can you improve on the parser qualities on extracting the tables? If you are improving the extraction and transformation job for the table, you might also solve the problem of the information lost. And so it depends. If you like to enhance approach 1 more, then you will also get to solve the same problem.
Yeah, it's like you have to do in multiple stages in the approach 1, but the approach 2 is like just send an image, get vector, store them, and do search and drag. So it's like the efforts and the building complexity. But yeah, it's still doable in approach 1 for sure. We are still working on the approach 1 to make it better for some of our customers. Yes.
Is this just an experiment, or is there supposed to be like an outcome that is usable for end users in the end?
You mean for the approach 1?
Yeah.
See, okay, so the approach 2, like we still don't have a working solution, because as I told you, the solution is there, but it's a workaround where we are doing this maximum summary ranking. It's not available in OpenSearch. But for the approach 1, yes, like we already have a solution. We have a GitHub code where like we can use how to use unstructured along with OpenSearch and do and have these connectors with extract and so on, so that you just pass PDF, it's gonna do all the layers of pre-processing and store it into OpenSearch. We have a sort of working solution, but needs to be fine-tuned. But for the approach 2, we don't have one. it's just like an experiment that we are still trying out. Maybe like once the feature is out for handling multi-vectors, then I think we might have like a solution, like a CloudFormation template for in AWS or a GitHub code repository to be used. But still, you have the demo notebook that you can go through.
More questions? Yeah.
No, I don't need that.
Yeah, we do so that the recording can capture it.
Oh, sorry.
Regarding the storage, so when you like send and retrieve, is there any cache? So you will save vectors, and what kind of cache do you use in this model, or it's like agnostic? Because, and then the first one is this one, cache one, saving the vectors, the embeddings. The other one is about the space, so how you optimize the space, because, you know, the dimensions, vector dimensions is huge. The approach one, or, okay, it's...
Yeah, see, when it comes to vectors, approach one or approach two, wherever you see vectors, everything is stored in memory. Everything is stored in memory in OpenSearch. So vectors are stored in memory, so that's why, like, you see, that's why you will see, like, when your vector search scales out a lot, when you ingest a lot of documents, then you will see a lot of resources that you need to provision in terms of memory for your cluster so that to support the vector search. So vector search is always on memory. Maybe you can have maybe like OpenSearch, the query cache and the other cache components can come in based upon the filters that you use on top of a vector search query, but everything runs on memory for vector search. The first search will be slower, but right from that, all the vectors are up in the memory. The graphs, the HNSW, the IVF clusters are in the memory, whatever the approach is. That's a question.
I'm Fernando from Zeta Alpha. We are also working heavily on ColPali in OpenSearch. A question for you is, how do you think we can handle showing the evidence back to the user? Because you know, in the traditional RAG, you can highlight the passage, and it's very easy for the user to verify if the answer was correct or not. But here you have this map, so it's not very clear. Yeah, just wondering if you have any ideas on this.
Yeah, see, leaving this image, you see here we are doing multi-vectors on an image, right? So leaving that, wherever you use multi-vectors, you have this, you get the interpretability of vectors, right? So like, what you can do is like, we work from the customers backwards. Say like, one of my customers had a requirement, like we want to highlight semantic search. That was one of the use cases that we had. And they were using BERT models already, okay? For their use case, it's BERT, the traditional BERT was working well. And like, since they wanted highlighting, like we suggested them ColBERT, and ColBERT was one of the multi-vector, again, this late interaction approach. It gives multiple token vectors, and in that case, documents like multiple token document vectors. So yeah, like ColBERT was something which just gave that highlighting capability. So I would say, like, based upon the customer's ask, first you can evaluate whether multi-vector is really required. So highlighting, it is required, and late interaction is always better than the traditional way of doing like no interaction models, right? So yeah, recall highlighting capabilities would be the key factor there to decide whether your customer needs, or your end user needs this multi-vector approach, ColPali or ColBERT, anything. So highlighting is something I'm seeing as a common ask.
I was thinking, because when you generate the query tokens for your query string, maybe it would be helpful to show to your customer that, oh, this is a query token that generated from the query string. We can also show that, and it also will increase some of the interpretability.
Yeah, so we also had something in text-based multi-vector approach. I can quickly show if that works. So here I'm using a ColBERT model for, oh, sorry, it's not vector search. It's keyword search, okay. Yeah, you see here, this is, I'm doing a vector search, and you can see like the highlighting on tokens, right? And this is because of multiple vectors of ColBERT. And it says like black, and the color code also says something. Here it says min gives the maximum score, and the light ones like little lesser than the contribution. So this was one of the use cases that we worked backwards, and we had the customer user using ColPort. So yeah.
Any more questions?
Yeah, please +1 on that RFC, like whoever is interested. Let's see this feature soon in OpenSearch.
If no more questions, then thanks everyone.
Get to lunch early.
Thanks for joining us today.